Yeah, hello and good day, and welcome to today's RFF-CMCC-NAVIGATE webinar. My name is Johannes Emmerling, and I'm a researcher at EIEE in Milan. And today we're going to have a webinar entitled "The Cost and Uncertainty of Climate Mitigation," and the main talk will be given by Detlef van Vuuren. Let me just start a few minutes explaining a bit about the Organizing Institute and the project this is related to. So we are here at the RFF-CMCC European Institute on Economics and the Environment, EIEE, which has been founded by the Italian European Euro-Mediterranean Centro on Climate Change on the one hand, and Resources for the Future in the US on the other hand. It is kind of a transatlantic partnership to work on economics of climate change and the environment in general. And we have been organizing this webinar series at CMCC since quite a while. And of course, during these times, webinars become even more suitable or practical. So we're happy to have another one on this interesting topic. This is also a webinar in the so-called Navigate webinar series. Navigate, which the title of the project you can see here, is a Horizon 2020 project funded by the European Commission, which basically aims at developing and applying a new generation of advanced integrated assessment models to support climate policy making. Just to give you an overview of the project, it's a project that started last year, and this looks at has three main pillars. One is looking at systems that are important for climate change mitigation transformation, looking at technology, energy, and the main macroeconomic transformations of the economy. The second one being looking at the people dimension of climate change and climate policies, focusing on spatial heterogeneity, inequality, and also climate change impacts, and including co-benefits such as air pollution and other SDGs. So it's quite a broad project and has a lot of modeling tools being developed and applied. And it also focuses on usability of such tools and outreach. And here, this webinar series has been perceived as one important outreach channel through which we can communicate and disseminate the results from our findings and our scientific publications. It is a huge project. Here you can just see the partner institutes and universities. And so we are very happy to have this webinar series organized jointly with this project. Just a note for our fellow listeners here, so that this webinar will be also recorded, and once it is finished, we will also upload it in the CMCC YouTube channel, so you can find it afterwards together with all the slides of our presenters on YouTube. And moreover, this Navigate webinar series will also be made available on the Navigate Horizon 2020 website, where you can see the URL here. Okay, but now let's turn to the topic of today's talk and webinar, which is the cost and uncertainty of climate change mitigation. The main speaker is Detlef van Vuuren, who is a senior researcher at PBL in the Netherlands and who is also a professor at Utrecht University. He is probably known to especially the scientists out here, as he is one of the most cited scientists in the top list of cited scientists worldwide. Has worked on many topics on sustainability, including very challenging topics such as biodiversity. And he started out his career, let's say, with a PhD thesis, which was on energy systems and actually long-term scenarios for an uncertain future. So this topic of today kind of speaks a bit, going back even to his PhD thesis, in which he also writes that that something like long-term projections are both necessary and difficult. So actually, we're tackling here an both relevant and also challenging topic. So that's why I think it's really interesting to have this presentation here. I think we learned quite a bit on the cost and uncertainties about climate and climate mitigation. So we are a bit different here today, compared to where we were in the past. But there's still a long way to go. So I'm very happy to hear his talk. And afterwards, we will have a discussant, and we're very happy also that Evelina Trutnevyte accepted invitation to also comment on this topic. She is an assistant professor at the Université de Genève, and she has also worked extensively on especially socio-technical systems, energy systems, and also decision-making and uncertainty. So I think we have quite some expertise on these topics here, and we're very happy to hear both of your interventions. So without further ado, and maybe just to mention that we will have both Detlef and Evelina's talk first, and after that you can, the audience can have questions and write them through the question tab in the GoToMeeting software, and I will pass them to both speakers to answer them after the talk. Okay, now without further ado, let's move to Detlef's presentation. And thanks for joining us. And Detlef, the floor is yours.
Thank you, Johannes. Let's see whether I can remove the viewer, which is now blocking my screen. But you can see my slides, right? Okay. Yeah. So the name of the presentation today, with the cost and uncertainty of climate mitigation, is quite ambitious, and clearly this will not be the final word on this topic, this presentation, but it is based on a paper that we published earlier this year in Nature Climate Change with a similar title. And the starting point of our work were actually the conclusions of IPCC AR5, where in working group 3, IPCC concluded that estimates of aggregate economic cost of mitigation vary widely and increase with the stringency of mitigation. And then they give a range of costs for reaching 450 ppm of 3 to 11%. And the underlying evidence is shown in that graph that I've included below. And indeed, here you would find different points of time and then increasing ambition. For each time period, the most ambitious graph to the right is showing that something that is comparable to 2 degrees. And you see that indeed there is a huge range of different estimates. All these dots represent different models, and estimates go from slightly negative up to more than 12% of loss of consumption. But this is not all. If we go to working group 1, we have to relate the 450 ppm CO2 to temperature. And there working group 1 says that 450 ppm CO2 not necessarily leads to 2 degrees, but actually to a range of about 0.3 to 1.7 degrees warming over the 1986-2005 base. And if you add then the warming that already happened in the past, this gives you a number somewhere in between 1.3 to over 2.5 degrees warming. And so taking that together, our question is, if we take these assessments of IPCC, well, what are the costs of reaching 2 degrees and 1.5 degrees? And given all these uncertainty numbers, what would be the real uncertainty range associated with these numbers? And what determines the uncertainty range? We have the economic uncertainty, and the physical uncertainty is one of them dominating. And so this is what we try to do in the paper that we published in Nature Climate Change. And to do this, we wanted to develop the most simple model of climate change, which had 2 elements. First of all, the socioeconomic part of the story, and secondly, the physical part of the story. And we didn't want to create a new real model. We simply wanted to develop a meta model that would be able to take the iconic messages of different parts of the IPCC report and bring them together. And so the first part, the first starting point was with the iconic graph that was published by working group 1, which is shown here, which on the one hand plots its cumulative CO2 emissions, and on the other hand, it publishes the the warming that comes out of, that is associated with that amount of cumulative CO2 emissions. And it's based on a whole set of runs with complex climate models. And what they found is that there is a near linear relationship with cumulative CO2 emissions and temperature increase. And it's based on the runs of the RCP scenarios at the time. Now we can use that graph to determine the carbon budget that is associated with a particular target. Let's, for instance, say 2 degrees. You could look up from the 2-degree point in this pink plume, what would be the amount of CO2 emissions that is associated with that. You could then subtract the amount that is already emitted and get a carbon budget. Now, clearly, this pink plume has a lot of uncertainty created by lots of different climate models that have been run, and so you could get different numbers of carbon budgets that are associated with the 2-degree target. Given the fact that this is a linear relationship, we can derive the linear equation that describes this relationship. And then the TCRE is the value that describes the shape of this curve. If you rewrite that, you can make an estimate of the carbon budget, and then you need the value for the TCRE, which was published by IPCC in 2014 as being somewhere between 0.12 and 0.62. And they also indicated that the uncertainty might be normal distributed or log normal distributed. We, in our model, we'll show it later, tested both assumptions, and it didn't matter too much, so we took the normal distribution, just like IPCC actually did. The second uncertain factor in this equation is the temperature in 2010, and also IPCC published on that. That the data that IPCC used was later revisited by Visser et al., and they gave an estimate for 2010 warming of 0.91. And they also indicated that there was an uncertainty associated with this number of 0.08. And and again, they indicated that there's a normal distribution, so we use that in our model. Now, if you take those numbers and then calculate what comes out of a simple model like that, you actually can really nicely represent that pink plume that is based on the empirical data of the climate models, and you get more or less the same outcome. So let's accept this. The next thing that we might want to have a look at is the non-CO2 gases, because that's actually already included in that particular model. It's based on climate model runs that have the non-CO2 gases. But obviously, the non-CO2 gas emissions are uncertain, and the runs that I've just shown are all based on the RCPs that have a particular relationship between non-CO2 gas emissions and CO2 emissions, and obviously, in reality, these are uncertain. So we took the IPCC 1.5 database and the SSPs and tried to find out what a relationship between cumulative CO2 emissions and the warming from the non-CO2 gases might look like. And if you plot that, you actually get, again, a rather linear relationship, to our surprise a bit. But you can understand why there is a relationship. So on the really right side, the high cumulative CO2 emissions coincide with a lot of warming from non-CO2 gases, and that's partly because they have the same driving forces. High population would lead to high energy demand, high CO2 emissions, but also high food demand, so relatively high emissions from N2O and methane, and also the high methane emissions from the large fossil fuel use. While on the left-hand side, these are mitigation scenarios. And so not only CO2 is reduced in those scenarios, but also there is policy for non-CO2, and therefore also the emissions from non-CO2 would be low. We actually expected some curvature on the low side in this equation. And the reason is that for non-CO2 gases, we know that it's relatively hard to really mitigate them to very low numbers. That obviously causes also this non-zero values at zero CO2 emissions, but the curvature is not that large, and we actually tested if we could find better relationship than a linear relationship. We hardly could find that, and it didn't matter a lot for our model. So we took the linear relationship. It has the nice advantage that in that case we can also simply assume that the impact of the uncertainty in the non-CO2 emissions is an error term on the already existing TCR equation. And we can estimate the size of this error term based on what this data that we have. And that would be, again, a number somewhere 0.14 to, in both directions that we can put on top of the TCR equation. We assumed here that this uncertainty would be normally distributed simply because it would be based on an independent set of variables compared to the CO2 emissions. So now I've focused on the biophysical side of the story, but I would now like to return to the economic side. And I actually would like to use, first of all, the same data that IPCC used, and which I showed on the very first graph. And IPCC in AR5 gave different metrics for estimating cost, simply because some models report cost in terms of abatement cost, other models provide consumption losses. Again, some models report GDP losses. And so what we did to make those comparable was look at the cost increase compared to going to 1.6 gigatons of CO2 as a target. And this is showing the results for that. And what you see is that moving from right to left, high CO2 emissions to low CO2 emissions, obviously cost of climate policy go up. You start to put more climate policy to avoid emissions. And you also see that the uncertainty starts to increase with a wide range on the very low side. And IPCC also gave a median value based on the literature, and confidence interval, and a full range. We checked whether, if we would use the SSP database, whether we would get a similar result. And again, here estimates are given in different metrics, so we normalize them again. And interestingly, also the SSP database has very, very comparable results to what was found by AR5. And so these are these individual dots here. And so we tried to find an equation that would represent this relationship, which was done by the equation shown on the screen. And we made 3 different relationships to represent the low side, the median side, and the high side, and could sample between these. And again, we assumed that there was a normal distribution we assumed in this case a log normal distribution that represents the uncertainty here. And the reason for choosing a log normal was that we could easily see that there was more evidence for relatively lower cost than for higher cost, as you can also see that the median is closer to the low end of the range. So now I have 2 models to represent the biophysical side of the story and the economic side of the story, so I can start combining them. And so if I combine them as shown here, I have all of a sudden a nice formula where I can calculate for Earth temperature target T, the cost that is associated with that, given the uncertainty in TCRE, the non-CO2 temperature, and the uncertainty in the different cost. And we use that to subsequently do Monte Carlo simulations. Now the model is extremely small, so we could do a lot of runs. In this case, we actually did 6,500 model runs. And this is the outcomes for the 2 sides of the story. On the one hand, the biophysical representation, on the right, the economic representation, and they nicely represent the underlying evidence that we used from the different parts of the IPCC report. Now, if we now combine these, before doing so, actually, I would like to show that you could potentially represent the biophysical part of the story also in a different way. You could, for instance, show the CO2 emissions associated with different temperature targets, and then instead of a single carbon budget value, you actually get a range of values that are consistent with a particular temperature target. And the nice thing about this presentation is that you then also see some estimate of the uncertainty associated with different carbon values, carbon budgets, which is quite large, and partly also explains why these carbon budgets change so quickly in between different estimates, because actually the uncertainty range is in these budgets compared to their actual value is comparable. But going back to the original representation that we had, and then combining them, I can easily now make a graph where I have temperature on one axis and the estimated cost on the other axis, as done here. And let's have a little bit more closer look to that. So first of all, we can easily see that the cost increases substantially for increasing targets, and especially on the high side of the results. The second thing that we observe is indeed there is a quite a large range in uncertainty range. It's about a factor 8 on the low side, and on the low side we find model runs that are consistent with the 1.5 degree target. On the high side we find model runs that are consistent with almost doing nothing, and then in between you have the 2 degree target. As I indicated, there's a factor 8 range. That's considerable, that's quite large. It may be not as excessive as you might have expected originally from the two individual estimates that I presented earlier from Working Group 1 and Working Group 2, but obviously now we have, with the probabilistic representation, you have to be really, really unlucky to be on the high side for both parts. But let's go a bit further here. So why is there a factor 8 range? So we can now do something nice with this small model, which is determine the impact of the uncertainty in each individual parameter, and then estimate its impacts on the total variance. And that can be done for all these different factors. This is based on a publication from Sobol et al. In 1990. And if we do this, we get this result. So I've now again plotted the temperature on the x-axis and the contribution of the different uncertainties of the individual parameters to the total variance on the y-axis. And what we see is quite interesting, because at high temperatures, let's first focus the non-CO2 sigma and the cost of both are representing socioeconomic uncertainty, and then obviously the 2010 temperature and the TCRE represent geophysical uncertainty. Now, something that is really interesting to observe is that for high temperature targets, the geophysical uncertainty really dominates our cost estimate. But if we start to move down to more policy relevant temperature targets, even at 2.5 degrees, the socioeconomic uncertainty starts to dominate everything. And certainly this is the case for the 2 degree and the 1.5 degree target. And so the uncertainty in our cost estimate is much more important for the cost of different climate targets than the uncertainty in the TCRE. The contribution of the 2010 uncertain 2010 temperature, and also the contribution of the non-CO2 emissions is also increasing, as we can expect. If the temperature gets close, the target gets closer to the existing temperature, and also we start to look to obviously then also the role of the 2010 temperature starts to become more important. However, the rapid increase in the contribution of the cost parameter more or less dwarfs the increasing impact of these other two parameters. But it's quite an interesting finding. So if we, for instance, want to try and reduce the uncertainty in our estimates, then obviously we can get a much bigger impact from reducing the uncertainty in our cost estimates than from reducing our understanding of TCRE. So costs play an overall dominant role in the uncertainty for stringent climate targets. You can also, by the way, already understand this by the fact that all the outcomes on the right side of these equations are mostly an uncertain climate. We are getting into worlds that have a 4-degree warming, and therefore the climate uncertainty is dominant. While on the left-hand side, we have totally changed our economy from a fossil economy to a zero-emitting economy, and so the uncertainty in the economy is much more dominant, while the climate stays more closer to the current one. So let's return back to the results of the model, and maybe focus a bit more on this large factor that determines the uncertainty. These are the socioeconomic parameters. So the model was partly based on the SSP database in terms of its cost estimates, and that gives us the nice opportunity then to look into which of these SSPs is actually giving what kind of cost, and that's shown now on the right. I've plotted here for SSP1 and SSP4. That's the scenarios with relatively low mitigation challenges that coincide with low population growth, high technology development, global cooperation. In green, I've estimated the cost for these scenarios, which are relatively low. On the other hand, for SSP3 and SSP5, these are scenarios that coincide with high population growth, little global cooperation, slow technology development. We see that the costs are relatively high. So that also means that maybe if you would look at the individual SSPs, that the cost for getting to 1.5 degrees under an SSP1 and SSP4 scenario is almost comparable to getting to 2 degrees for an SSP 3 and 5. So we can now try to unpack that socioeconomic, that cost uncertainty, and see that the socioeconomic development is actually a very dominant factor here. We can unpack it a bit further, and here I'm using the assumptions of a single model, actually an expanded version of the model that I've been presenting that up to now, but a version where we also added learning, inertia, and negative and different assumptions on negative emissions, and we calibrated also that model against the available literature, and we could easily show that also the representation of technology development, whether inertia play a big role and whether we allow negative emissions, have quite a considerable impact on that socioeconomic part of the cost. So I've shown so far that costs are getting higher on the low end, and so one might start to worry whether those costs will be still smaller than the benefits of climate change. And while this was not part of that paper, we are now trying to further expand that small model to also try and say something about that. I'm not going to discuss that in a lot of detail now, but I would like to show at least one of the results of that exercise to comfort you in trying to see whether climate change is still worthwhile. So what we have done now is used on the one hand the equation on the mitigation cost and combine it with estimates of climate damage. And climate damage is also uncertain, of course. And here we use 3 different estimates. One is the DICE estimates. That's the estimates that are used by the model that was made by Bill Nordhaus, which are relatively small. Then we have a second set of estimates based on a paper of Howard, and a third set of estimates which are based on a paper by Burke et al., and those are relatively high. And we then combine the mitigation cost uncertainty with all the parameters that were already shown here. So including, for instance, the uncertainty in TCRE, including the uncertainty in the mitigation cost and the 2010 temperature. And we combine it with these damage curves. And it also meant that we had to add a small growth model to this equations. And the outcome is shown here. And so on the x-axis, we have the mitigation cost. On the y-axis, we have the avoided damages. And you can put in a line where the costs are equal to the damages. And if you're above this line, obviously, climate policy would be attractive. If you're below the line, climate policy is absolutely not attractive. And what we find here is that if we have the DICE cost curve, clearly our mitigation cost would be larger than the avoided damages. And so for an economic perspective only, climate policy would not be worthwhile. But for all the other cost curves that we looked at, and given all the uncertainty still in the cost and the TCRE and the 2010 value and the contribution of the non-CO2 gases, almost in all cases, actually we found a positive result from the climate policy. It would avoid more damages than the cost of the climate policy. So my last two slides. So first of all, on the model. So the model that I presented here is nicely transparent. It can be easily calibrated to the iconic assessment findings. That's what's actually the purpose of this model. Can we simply combine different parts of the IPCC report and represent the literature and not add just another model to the literature, but try to be calibrated to the full literature range. And obviously, this model has some clear limitations, mostly due to the fact that it's a meta model. The code is available, but actually, if people want to use it, you can directly take the equations and the input data from the article. It's really simple. And it can be easily expanded. So first of all, based on the literature in work group 1, you could break up the TCRE further into an uncertainty for carbon cycle and climate sensitivity. In addition to what we have now done for the non-CO2 and just look at the emission parameter, people could also take the uncertainty in the forcing as an additional parameter to look into. You probably need to then also recalibrate the TCRE, but it can be easily done. Then you could also make add a time dimension to the model, plus not in yet, and for instance, add some other economic choices and uncertainties like the technology learning, the inertia, the discount rate, and see how those contribute to the full uncertainty range. And so, you could also, as we already did, add damage curves. Sorry, I put the Dutch word here, and show how, and make this into a small cost-benefit tool. And there might be lots of other things that you could easily do with this simple model, and move a little bit from the scale from very simple to slightly more complex. Now, in terms of conclusions that could be taken from this presentation. So first of all, I would like to say two things on the type of analysis. In the work on and the outcomes of integrated assessment models, we are so far quite reluctant to make statistical interpretations of the outcomes of multiple models and different studies. And I think that we might want to try and do this a bit more. And I think, so clearly this was done in this particular presentation, but I think it does add value to our, the way that we normally present our data. I also think that we can do a bit more with meta modeling, and I hope I have shown that in this presentation. What the model clearly shows is that there are rapidly increasing costs for low temperature targets, but mostly for the high end of this uncertainty range, so only for SSP5 and SSP3. on the low end, on the SSP1 and SSP4, actually the increase was much more modest. The uncertainty is considerable, but it doesn't seem to be as excessive as you might have based on the two statements that were on the very first slide separately for working group 1 and working group 3. And what we have also shown is that the uncertainty is dominated by the socioeconomic parameters and especially the underlying SSPs. And so if one wants to reduce uncertainty, you might want to invest more into research related to those parameters than try to reduce the uncertainty in the CCRE more, because that's only relevant for scenarios that have a lot of warming. That's where I would like to end. And at this point, I would like to give the floor back to, I guess, to Evelina. And I can do that.
Thank you very much, Detlef. I hope you can see my screen. So I would like to, yeah, thanks so much. I would like to add a couple of reflections on Detlef's presentation, and especially with the methodological focus, because there's a clear added value of the study. First of all, it's a new meta model. It also allows to bridge the climate models and the integrated assessment models, and allows the more extensive uncertainty analysis. Now, when we look into uncertainty and uncertainty quantification in particular, what becomes really also important is the time horizon. So if we are thinking in the years like 2020 or 2030, it's like in this image, you know, we can see it rather crisp, what could happen, even if the uncertainties are quite wide. But then when we extend to these scales of 100 to 2100, it becomes less and less visible, and eventually it's really just this blur or a cloud where we more or less can see perhaps a shape and some edges there. So actually, if I would like to borrow here some concepts of Kasman and colleagues, but this shows the weight that one can add on the different models to analyze the various timescales. So when we work with more detailed models, we can, and perhaps even a single model, we can be more confident at these short timescales. But the metal model example, like Detlef showed, because it becomes a simpler model drawing on many different types of models and scenarios, it's probably kind of, I think it would fit more these even longer timescales where we would want to, and we would be able to somewhat estimate the trends, but also already put way more emphasis on the uncertainty analysis. And then, of course, when we think on a very, very long time scales, this becomes the kind of scope of the so-called bounding analysis, where we can only more reasonably estimate the upper or lower bounds to give kind of the shape, so to give the corners of the shape of this cloud. And so in this case, these meta models, in my view, can really play an important part in the climate policy analysis. Now, the second reflection is on whether the diversity of models that is used for, let's say, this meta modeling example is sufficient. And here I would just like to bring kind of a snapshot of some of the analysis that we have done. So we pulled together, as you can see here, over 1,550 scenarios, systematically selected, and it's on solar photovoltaic projection. So it's not on the overall kind of climate mitigation challenge, it's on one technology globally. And there we had 190 peer-reviewed and as well influential grey publications, as well as 2 of the IPCC IR5 and 1.5 degree report databases that were also used in Detlef's study. And for example, already looking at this one technology, as we can see here, just by drawing the kind of modeled solar PV generation to the year 2050, these IPCC, so scenarios in the IPCC databases, we can see they already represent relatively well the uncertainty. And of course, there's a large number of scenarios in these databases. And yet there is a little bit more in terms of at least PV projections, kind of the non-IPCC databases is still a little bit kind of has longer tails, especially on the higher end. Then if we kind of dig more into this in detail, and here we spoke about the costs of mitigation, so we can see here two graphs on the cost of 1 kilowatt of PV with respect to what is the projected growth rate of solar photovoltaic that is in these scenarios. And well, we can see, as shown also in the previous graph, that somewhat the range of the growth rate is comparable between the two subsets. We can see that the cost estimates are much higher, and this is a logarithmic scale in the IPCC case than non-IPCC case. And I think in this case, it would, I think the question is whether really the diversity is sufficient in this model, and how we could improve it by bringing the other types of assessments that come maybe from a bit more disciplinary or technology specific literature and come from very different types of models and different types of even analysis, but how we could incorporate that into meta models and more broadly into climate policy assessments to have a more complete range of uncertainty. And here I am finished, and I will now give, I think I have to.
Yes, if you can give it back to me, that's great.
I have to figure out how to do it. So, 1 second.
Okay, thank you very much, Detlef and Evelina, for these great presentations. Yes, so I think maybe Detlef, if you want to have some comments on some of these, I think, interesting points raised by Evelina. And in the meantime, all the people on the computer or in their meeting rooms, you can write questions using the question tab, which I then will pass on to the speakers. So please just write it in the question box.
Yeah, I liked Evelina's response a lot. I think indeed in her first remarks, she really pointed out why it is useful to start thinking also of meta models in addition to the rather detailed models that we normally use to make long-term projections. And often the type of questions that we want to explore for these long-term, in the long term, are not really about individual technologies and things like that. And so that's why I did think these meta models really help to, on the one hand, answer the questions that are relevant on this time frame, and at the same time do justice to the increasing amount of uncertainty. And I think the second remark was really useful too. In our analysis, we deliberately wanted to focus on the information that was brought forward to IPCC because we wanted to combine the different messages from the different parts of the report. But yeah, obviously you could also train meta models on a wider set of information. And if for this particular model, you would have estimates on ranges and an estimate on the different distributions, how the forms of the distribution, you could easily take another source of information than just the models. And I think that this is something that we absolutely would need to do. It's to some degree also comparable to what Working Group 1 needs to do when it's looking at estimates of climate sensitivity. On the one hand, it would use climate models to estimate that, but it would also look at information on the climate system from other sources, like paleo data or historically observed warming, and compare it, how those ranges look like, and then finally make an overall assessment. And something similar might be useful to do here as well. So for cost parameters or PV expansion, to look at what the models say and then take other literature, make an estimate of the realistic range and also the form of the underlying uncertainty.
Okay, thanks. Yes, maybe let me start with a question that was raised, I think, to Detlef about the socioeconomic factors that you were saying and also play an important role, and this uncertainty around them. What did you exactly consider there for this? Which socioeconomic drivers? And also, the analysis seemed to be done on the global level, right? So how do you take into account, I mean, is there any consideration of non-global, I mean, more disaggregated levels, or how is it done?
Yeah, so here we wanted to focus clearly on a global question, and so yes, this model is extremely simple and doesn't have regions. But it is using data on much more detailed models, and so, for instance, on the cost estimates, we're using partly the SSP data. We are using data that was used in AR5, and those are based on IEM model runs that have much more detail in terms of regions. And so in principle, you could also take that regional cost information and bring that, if you want to, separate into a meta model. In terms of the uncertainty, so first of all, if we train the model on the AR5 database, you have a very wide range of scenarios where we actually don't know exactly what is causing the differences in cost. So some models might be it might be really expensive to mitigate by itself. It might be not so hopeful in the assumptions on PV cost decrease. But at the same time, it could also be caused by the fact that that model was assuming very high population growth. And that's why that second calibration to the SSP data set was quite interesting, because there we know much better what is causing the differences. And because from 6 different models, we have 5 different sets of scenarios, and we can derive cost estimates for scenarios where there is a relatively low population growth, and a lifestyle that is more consistent with sustainable development, and see the impact of that compared to particularly high population growth, little cooperation. And so that's why I also showed the difference in the SSP1 versus SSP5 results. And that turned out to be really an important factor, probably much more important than the uncertainty within the SSP.
Yeah, good points. A similar question in this direction about the timing. So about, is there any taken into consideration of the cost of delayed climate action, given that you only have one time step, basically?
Yeah, so here it didn't, because we picked up the full century cost. And so this model doesn't say anything on timing. It's using mostly these cost optimal scenarios. But obviously timing is a really, really important factor. Uncertainty and decision in mitigation action. And so we did further develop the meta model. We now have a version where we also look at costs over time. So yes, and then we can also play, for instance, with the discount rate and see how cost optimal pathways depend on how you discount the future, or, for instance, on your assumptions on negative emissions, and allowing the model to have negative emissions or not have quite some consequences where how you would time your optimal response. So I 100% agree that this is a critical issue, but in this particular paper, it didn't play any role.
And one question about this, the kind of CBA interpretation. From the graph where you compare the costs and climate impact, it seemed that 2 degrees would pass maybe kind of a cost-benefit test, whereas for 1.5 degrees is not clear and there's higher uncertainty. Would you agree, or what? I mean, it's preliminary results, but yeah, what is your...
Yeah, I do agree. And obviously, here for the 2 degrees, I could easily show that for both Howard and Burke, we would pass the test, and only in the case of dice runs, it would be more iffy. But for 1.5, that relationship obviously started to change. The Burke damage curves would easily still pass cost-benefit test. But then it starts to be dependent more on the other uncertainties like discounting. Obviously, you also have to remember that the damage curves are only one representation of what we value in terms of damages for climate change, and there might be also other reasons.
Okay, here's another a bit maybe provocative question. To Ben Matthews, this reminds to the IPCC third assessment report. So the question is, what has been evolved in terms of this uncertainty since then? Was there big progress in uncertainty, or is it still similar? What would be your, opinion on that? I think.
So personally, I think there is absolutely progress. The TCRE was a major step forward. I think also in terms of communication. So I think we are much better able to communicate some of the major uncertainties to policymakers. I think also the models have improved, and so the way that we now can start to unpack the different parts of the socioeconomic uncertainty is beyond what we could do in the third assessment report. That first of all, for instance, with this disentangling of the different socioeconomic parameters, scenarios, the SSPs.
Yeah, okay. Two small questions about, is there any way that you think you could do some validation exercise on said model? Is there some way? And also about this interaction effect when you compare these, I mean, do you look into the interaction effect of the different sources of uncertainty, and how is it computed on? What did you find interesting there?
So this interaction effect obviously was relatively small, and so that's why we focused more on the individual parameters. Can you remind me of the first part of the question?
Yeah, the validation. I mean, is there a way to validate? I mean, would there be a way?
Yeah, so real validation is obviously a bit hard. On the climate part of the story, validation of the big models that underlie the estimates here is still possible, because these models are also run in the past. For the socioeconomic models, it becomes already more difficult, because there's no guarantee that the future needs to be as the past. By the way, Evelina has done quite some interesting work where she used IAM models and run it over an historical period and showed how that compared to the past. Maybe Evelina wants to say in a second something on this particular topic as well. On the uncertainty part, that would be really hard to really do a validation. The only thing that I wanted to show is that to some degree the outcomes are a little bit as you can expect, with a very dominant part coming from the climate part for high temperature, for high climate change, and a larger part coming from the socioeconomic uncertainty. We did not expect that socioeconomic uncertainty to be so dominant on the low temperature targets. It was much more dependent on the temperature than as we had expected. But maybe Evelina, you would like to say something on the validation.
Mm-hmm. Yeah, of course, there's one main challenge in validation of global models is that there's one globe only and one history that we can look at. Right. So very often the validation kind of ends up in trying to make the model replicate the past pattern, which may not be necessarily a good measure for the future. So at least in our experience, what can work a bit better is actually using different model formulations. and testing them kind of on retrospective data analysis, in a sense, to find out what model formulation does perform best. And I really mean about different types of models, so really structural uncertainty rather than just feeding different data or making tweaks in the model. So yeah, that is one of the ways to overcome this single globe problem.
Yeah. So validation might be challenging, another question about it, but let's maybe move, in sake of time, to two more short questions. One very quick about whether the code of the meta model is kind of be made available. And then finally a question about the economic part. So taking this further, what would be, based on this model, let's say the cost minimizing carbon price? You could probably, estimate the optimal carbon price, and also carbon price trajectory. What would be your policy recommendation for, based for an economist advising on carbon pricing based on this model?
Yeah. So quickly, we actually did further develop the model. And those papers are still under review, but the code of the more developed models will be made available also directly when those papers are published. For this model, it is available, but it's more or less, you can take everything out from the paper itself as well. There's no lot of added value. It's that simple. With hindsight, actually, when we had published, I actually thought that maybe it would have been much more interesting to focus more on the carbon price already in this particular paper. I think it's a more easily understandable parameter than this overall cost estimates that we focused on. We do now, with this time-dependent version of this model, quite some experiments with carbon prices, and especially looking into the question whether, in what case the hoteling rule is an optimal result, or whether in what cases you would find different pathways. And for instance, if you want to avoid negative emissions, the hoteling rules result is not a logical outcome. But also, depending on your assumptions on inertia and for instance, learning, you might find different pathways.
Okay. I think we're almost at 4, so I would close the Q&A session here. Thanks everyone for asking, and thank you very much for Detlef and Evelina to answering these questions. Just to wrap it up, we have, of course, the next webinar on CMCC, on which you find the title here, the 22nd of September. And we also have the next NAVIGATE webinar, which will be on the 19th of November. It has just been confirmed, and it will be on the influence of impacts and mitigation costs on inequality. So a bit related topic on the 19th of November. And just a final word that we are also, together with the 5 other institutions, launching this new webinar series called SWIIP Sweep on environmental and energy economics and policy. This is also some further webinars that you might be interested in and will be informed about. And with that, I think we are done here. Thanks everyone for participating, and a special thanks to our speakers, and hope to see you soon in the next webinar.